Hey, welcome to the Cosmic Pie podcast, coming to you from the campus of the University of North Dakota. So I'm Wayne Barkhouse, and along with me here is...
Robert Moore. Nice to see everybody again.
Okay, just before we start, I'd just like to mention that please participate in our live chat. So if you have any outstanding or even not so outstanding questions to ask us, please feel free to put them in the live chat, and we'll do our best to answer them. And if we don't know the answer, we will make something up. Right, Robert?
Well, I would prefer to say we don't know, but we'll find out for next week.
There, that's a good way of addressing that. Now, talking about making things up.
Oh, Lord.
One of the things we've been looking at over the last week is the way that we communicate science to the general public. And what I mean by that is the titles of articles that we put on the web mainly, really as a way to try to get people to click on that link.
Yep.
And so clickbait, I guess, is the proper term.
I hate calling it that because, they have a legitimate reason for doing what they're doing. But I think I'll come back to that.
Okay.
First, let's look at a few headlines. What do you think?
That sounds good.
All right. So I've got a few that I found from recent articles on science. And so we've got piece of the sun breaks off near its north pole, leaving scientists stunned. Astronomers discovered the impossible about the universe. This is coming from CBS. Dwarf planet Quar has a ring system that defies our understanding of gravity. Yahoo.com, so not exactly the greatest news source there, but,
Hold. I get to interrupt, Robert.
Okay.
This is the point where we have to issue that disclaimer.
Yes.
Any of the opinions expressed by Robert and I are solely the opinions of Robert and I, and not necessarily the University of North Dakota, the College of Arts and Sciences, and the Department of Physics and Astrophysics. Okay, Robert, proceed.
Okay, now I'll proceed. So my point that I'm trying to make is very rarely are scientists stunned or astounded or something defying our understanding of gravity. In the case of that story, the rings were just in a place that we weren't expecting rings. We expect rings to be inside of a radius of the planet called the Roche limit because they're being broken up, into smaller and smaller chunks. That happens inside the Roche limit. These rings are outside of it. It's got nothing to do with it breaking gravity. It's got to do with, what are they doing there? So it's an interesting thing, but it's not something that defies our understanding of gravity. So what I'm getting at is they have a purpose with all of this, and they're doing their job. You see this and you click on it. And most of us, actually, we don't click on it. We just read that headline and go, well, I saw where scientists didn't know what was going on. I don't know about you, Wayne, but there's very rarely that I see something that I'm just like, holy crap, that changes everything.
Well, I mean, if we look specifically at the ring system, it wasn't that long ago, really the time before the space age, where we thought that Saturn was the only planet in our solar system that had a ring system. In fact, we've discovered that in the 1600s. Cassini was the one that discovered that. Galileo has seen something odd about Saturn through his telescope, but he never quite had the resolution, the clarity with his instrument to be able to say that is a ring that's around Saturn. So he knew that, and in fact, he wrote in his book that it looked like that Saturn had two teacup handles on either side of the planet. But
Right.
he quite didn't get it that it was a ring system. But so we've known about the rings around Saturn then from the 1600s, and it was really when you get close to the space age, we started sending Pioneer spacecraft past Jupiter and Saturn, and the Voyager 1 and 2, and so on. So we know it today, and also from ground-based observations that was done by an occulting of a star by the ring system. So we watched a planet, and a star just happened to pass behind the planet relative to the Earth. And what we discovered was that certain stars, they would blink on and off as the ring system passed between the star and us, and then finally the star would be occulted by the planet, and then back out the other side. If the alignment was right, you'd see the other side of the ring system. So now, of the major planets in our solar system, we know Jupiter has a ring. Saturn, of course, we knew about that for a while. Uranus has a ring, and Neptune has a ring. So now, all of a sudden, planetary ring systems, or ring systems in general, are not so unique any longer.
Right.
So to start to find, anywhere where you have debris laying around potentially, and that debris is able to orbit in a fairly long enough type of stable orbit that it gives us a chance to observe. It's not like it doesn't exist for like a day or two and then disappears. The chance of capturing that by us, of course, would be pretty small statistically.
Minuscule, right.
Yeah. And so we're starting to see these type of systems. In fact, I remember a report that came out a long time ago where scientists speculated that even the Earth in the distant past, and by distance I mean several 100 million years if I remember the report, might have had a ring system.
Right.
And that material then eventually entered the Earth's atmosphere.
And in fact, I would hazard a guess, due to some of the impacts on the moon, that Earth has intermittently had ring systems. Because some of those craters are pretty large. They would have blasted off material that would have gone into orbit around both the moon and some of it around Earth, and we would have a ring system.
Well, it makes you wonder if some of those linear-like craters that we see,
Mm-hmm.
and sometimes we think of those as being like a double impact of an asteroid, let's say, on the moon and other places. That I wonder if we could get that scenario where a lot of this debris is raining in at some point and causing impacts, and they're
Right.
along this line because that's just the orbital path of that debris.
Right.
And you don't even need it to fall all at the same time. You need it just to come in at within several millions of years or so, because if it's on a body like the moon, you don't have to worry about the erosion from rain and wind and so on. And so therefore you could get then these parallel tracks, if you like, these linear-like features of these impact regions.
Right.
And so that's a possibility.
I agree. And so, some of these things, okay, I'll get it back to where we were, which is Quar has a ring system. And it's not where we would expect a ring system, but it doesn't break gravity, okay? And that's what all these headlines are about. They're out to grab your attention so that you're more likely to click that link. But that's their job, to make you click those links. That's how they make their money, is you reading so they can sell advertising dollars. So I get what they're doing. I just wish they would be, a little less sensational, a little less dishonest about things. Because I'm going to switch back here for a second. Mizzou wanted to see us. But we get things like this, which leads into another topic we'll discuss here in a moment. These new Webb telescope images are universe breakers, say baffled scientists. Except they're not. But that's where I'm going to turn it back over to you. You have some input on these studies that's referring to.
Right. So the latest study that came out just a few days ago is the report that there are some massive galaxies that exist. So literally, up to about 500 million years on average after the Big Bang event itself. And so one of the things that we're interested in as astronomers is trying to understand the whole process of galaxy formation. There are different types of galaxies. There's not just galaxies like our own Milky Way. And we divide galaxies into different morphological classes. For example, there are galaxies like the Milky Way, spiral galaxies. Mm-hmm. There are galaxies that are not like the Milky Way, like elliptical galaxies. There are irregulars. There's S-zeros. And so there are different types of galaxies, but you could ask the question, why isn't there just one type? What drives the fact that there's several different types? Yeah. And they're distinctively different from each other, and they're not even close, most of them, right? So we have, a broad or coarse understanding of where the different types of galaxies come from. Do we know all aspects of galaxy formation? Do we know precisely how you form one type of galaxy versus another? Given the initial conditions and all of these things? No, we don't know exactly. But what we try to fit in, of course, is the whole idea of galaxy formation within the context of cosmology, the understanding of our universe. We know that the early universe was very dense and very hot. And there's no way around that. Okay? Right. Those come directly from observations, right? For example, the cosmic microwave background, even if there wasn't a Big Bang, the early universe had to be dense and had to be very hot. In fact, there were alternative ideas to cosmology.
Right. I want to point out that the reason the cosmic microwave background says that it's hot and was dense is because it exists in the first place. If the universe was as it is right now, there would be no no radiation coming from everywhere, which is what the cosmic microwave background is. It's everywhere you look. It's the same temperature. It's the same signal. That can't happen unless the universe was once very small, much smaller, much denser, much hotter.
Yeah, very denser and very hot. I wouldn't never use the adjective smaller.
Okay.
Because there's
Fair point.
always that one scenario, and we don't know the answer to this, where the universe can be infinite in extent spatially.
Right.
And so if you have an infinite universe, if that is the type of universe we live in, like I said, we don't know, then if you cut infinity in half, each of your pieces, how large are those, Robert?
Oh, well, there's still infinity.
Right. So if you do half a half a half a half a half a half of infinity, right, you still have infinity as your
Right.
pieces. So the universe can be dense, but still infinite in extent.
Okay.
So
I get what you're saying now.
right. So the cosmic microwave background, a good way of thinking about it is the leftover heat
Right.
from, and in this case, we think, there's a consistency. We think that it's the Big Bang as the terminology that we put to the creation event of our universe. But there's room there for flexibility and all of that, of course.
Mm-hmm.
But we know the early universe had to be very dense and very hot. If the Big Bang is the correct model, if there is a finite time in the past where the universe began, and if that's the case, that is approximately 13.8 billion years ago.
Right.
Okay? We're seeing these massive galaxies, presumably, come in existence within the first 500 million years, 500 million years of the Big Bang itself. Now, is that possible? So let's go down this rabbit hole just a little bit.
Ooh,
Okay.
This is a rabbit hole.
So bear with me, okay? So as we get closer to the beginning of the universe, and this is assuming the standard Big Bang cosmology, okay, the universe gets hotter and hotter and hotter and hotter. It gets to a point approximately 400,000 years after the Big Bang. And in that time, by the way, the universe has been expanding. How do we know the universe is expanding? Because we can measure the expansion of the universe. That's something that we did about 100 years ago.
We can see it, folks.
Yeah. So whatever your ideas, whatever your hypothesis that you put together to try to describe the universe as a whole, it better also describe the expansion of the universe because that's observable. Anybody can see that if you have the telescopes that you need to be able to look at distant galaxies and see that they're all receding away from every point in space, including us. They all display what we call a redshift. So in the past, we've talked about the Doppler effect.
Right.
The fact if a source of waves is moving away from us, the wavelengths get longer or stretched out compared to if that source is stationary relative to us. Mm-hmm. So when we go beyond our local region in space and look at galaxies, in particular we look at their spectra, we see that their spectral lines are all shifted to the long side, a longer wavelength than what they would have if the source was stationary relative to us.
Right.
And the other thing that goes with that is the further away a galaxy is from us, the faster it's moving away. That's the effect of the expansion.
Right.
Okay. So with that scenario then, we know that as you proceed from the Big Bang event itself and go forward in time, the universe expands, and along with that, the material separates out. So it fills up an ever larger volume of space, so the density goes down. Along with that is a decrease in temperature. Mm-hmm. Now, for those of you who are unfamiliar with how density and temperature are related to each other, one of the things you might have noticed is in the springtime. So we go through a long winter here in North Dakota. When spring finally gets here in July, no, just kidding. When spring finally gets here, let's say in April or May, one of the things that some of us like to do is get on our bicycle and go for a drive, go for a ride, right? Mm-hmm. And so what we do then, what we do is check the air pressure in our tires, and chances are that it needs to be topped up, after sitting around all winter. And one of the things you might have noticed if you put air in your bicycle tires and then grab a hold of the sidewall of the tire, you'll feel a slight warming. And so what has happened is you've increased the density of the air inside of your tire. That's what we mean by increasing the pressure, the tire pressure. And that, along with that, comes an increase in the temperature.
Right.
Okay? Now, if you do the reverse of that, if you take that air and let it fill up an ever larger volume, then the temperature will go down. Okay? And we're just talking about normal things like air, right? In this case, we're not talking about anything exotic that's not ideal gas type of stuff. And so in that case, and if you think of the universe, if you apply it to that, as the universe expands and fills up an ever larger volume of space, we expect the temperature to go down, okay? So early on, the temperature was extremely hot. Now, one problem with the Big Bang, and this is a problem that it's always had from the beginning, no pun intended, is that when you go back in time to the moment of the Big Bang, really what you're heading into is where temperature approaches infinity, right? The density goes to infinity. Even if the volume is infinite in size, right? You still have an infinite temperature and an infinite density. It's really telling us as our known laws of physics break down at that point, where in such extreme conditions, we don't have a good understanding of what happens there.
We're in a position where what is temperature, what is position, what is density, all of these definitions that we have in the modern epoch break down. They go away.
Yeah, even our notion of time
breaks down.
Because people always like to ask that question because they know it gets cosmologists is what happened before the Big Bang. Well, if you use that word before, that's a time
constraint.
And so it's like
time
asking,
went away.
did time even exist before the Big Bang? So Stephen Hawking was always famous for saying, well, asking what happened before the Big Bang is like asking what's north of the North Pole. It's a meaningless question if time begins at the moment of the Big Bang.
Right.
Okay?
That's what I use for that expression.
Yeah, so if we go then forward from the Big Bang, then the temperature drops. Eventually it gets to a point where the temperature drops below about 3,000 Kelvin. That's approximately the same temperature in Celsius and Fahrenheit. It's just differ by a couple hundred degrees, okay? So roughly 3,000 Fahrenheit. When the temperature drops below that, then what happens is that ordinary matter can form, like hydrogen atoms. So a proton and electron combine together. There's no energetic photons immediately available to break those particles away from each other to break apart the hydrogen atom. So we can start forming normal material. And the temperature continues to drop as time proceeds forward direction. And we start, populating different things. Helium can form and so on. And so that means we have to wait for a certain period of time after the Big Bang before it's conducive for the formation of structure. That would include stars and also, of course, galaxies. And so we know we can't form stars prior to about 400,000 years after the Big Bang. Earlier than that, it's just too hot of an environment. Okay, If we had a hydrogen atom that existed, let's say, 1,000 years after the Big Bang, it would just be destroyed in a very short period of time because of all the high energy photons around.
It would have been dissociated into an electron and a proton.
Right. And so if we wait long enough then, and the universe becomes cool enough, then we can start forming structure like galaxies. So the question is then, when can we start forming structure? Well, it'll have to be after the temperature drops below 3,000 Kelvin, which means more than 400,000 years after the Big Bang. But when do we form stars, and does gravity do its thing to cause galaxies to form? That's always been a question. And a lot of the times what we do is just say, it probably takes about 1 billion years. Now, why 1 billion years? Because it's a nice round number.
Right.
It's not like it's written on a stone and was handed down to us 1 billion years.
And I'd like to point out, until James Webb, we had no way of testing that. We couldn't see far enough back into the universe. So, it is one of those times when the galaxies and stars start forming. We didn't know, but we had some good guesses.
Yeah, we have obviously had the Hubble Space Telescope in orbit for several decades now, and the Hubble Space Telescope allows us to observe at a very large distance from us, therefore go back in time, and so we can put some constraints on when galaxies appeared to form, but we didn't get to the epoch of galaxy formation.
Right.
We didn't get to a point in our observations where we could say, hey, I don't see any more galaxies. That must mean that galaxies haven't had a chance to form yet. And so with the James Webb Space Telescope, we can get back to the point literally 500 million years, so 500 million years after the Big Bang, and we see the presence of some large, massive galaxies. Now, there's one little caveat in all this, is that we don't have a very accurate measurement of what we call the redshift of the galaxies. That's done through analysis of their spectrum. So we need spectroscopic measurements of these galaxies in order to confirm their redshifts. In other words, their distances. In other words, the time that we're seeing them now.
Right.
Because that light left those galaxies more than 13 billion years ago. But was it 13.4 billion years ago? Was it 13.5 billion years ago? We don't know exactly because we need to get a measurement of their spectra. So that's yet to come.
That's yet to come. And to me, that's the important part. That's the really important. We haven't confirmed that these are that far away, that they're that far back in time until we get that spectrum.
Right. So let's, for the sake of this podcast, let's assume that spectra will, follow-up measurements will demonstrate conclusively that, yes, these galaxies are at a distance such that we're seeing them at 500 million years after the Big Bang. Does that mean the Big Bang is now wrong, Robert?
Absolutely not. Absolutely not. The Big Bang, as a theory, still predicts, and the observed quantities of hydrogen and helium that are in the universe, it still predicts the cosmic microwave background that has been observed. It still predicts a laundry list.
Expansion of the universe?
The expansion of the universe. You know, the list goes on and on. It fits the observations that we see in the universe. So the Big Bang theory is not in question at all, no matter what anybody else tells you.
Right. So the whole idea behind the James Webb Space Telescope in the initial concept, and the reason why the telescope is designed to make observations at infrared wavelengths, was to look at these objects like early forming galaxies in the high redshift universe, in the distant early phase of our universe. That's what it was earmarked for. So we would say in astronomy that the cosmologists designed the telescope to the chagrin sometimes of stellar astronomers who maybe wanted to use it.
Or us planetary folk.
Yeah, who would use it for other things. But that was the design, right, of the telescope. And so it was, so why would you go to all this trouble of spending literally, we know, billions of dollars now on this telescope and all of the work effort that was involved in the time it took to build the telescope and get it into space? Why would you go through that whole enterprise if you knew all about galaxy formation?
Right.
You see?
The answer is, of course, you wouldn't.
Yeah.
You'd put that money to look at something else.
Right.
So.
And in fact, if you did a simple diagram, maybe I should have brought that with us today, of looking at what happens, the major phases to the universe since the beginning, one of those phases is known as the Dark Ages. There's a question mark there. That was the era or the epoch of galaxy formation, and it was always labeled as a question mark.
We just didn't know. We had no data, no information.
That's right. So we expect to get some discoveries. We expect to be surprised in all of this, right? We're looking in a new part, if you like, a new time period of our universe with the James Webb Space Telescope. In fact, if we didn't find something unusual or surprising, it would have been a great disappointment in that sense.
It would also have been an incredible surprise because, again, we had the math that was saying, hey, we could do this. We had some very good reasons for saying, oh, this is what was going on and what happened. But we hadn't seen it. We hadn't observed it. We hadn't measured it. So that's what James Webb is allowing us to do. And lo and behold, there's some surprises.
So when these observations get confirmed, then who are the select group of people that need to pull out the proverbial pencil, sharpen the end, and get down to work?
Well, it's not cosmologists. I would have to say it's probably the galaxy formation people.
It's the galaxy formation scientists. Those are the ones that are going to have to revamp their understanding of how galaxies form and how the different types of galaxies form and the time required for these galaxies to form. So that's something we need to look at closely. Right.
So you want to show them the pictures of these galaxies? So this is what we're looking at from James Webb. Those nice little reddish, orangish dots. So it's not even a matter that James Webb has the resolution to see these things, whether they're spirals or ellipticals or what type of galaxy they are. It's a red dot.
Well, if you look at each of the postage stamps, so there's three at the top, three in the bottom, and in the middle of each of those postage stamps are these candidate high redshift massive galaxies that the study is about. And so what we need is to confirm, of course, their redshifts, to know what distance they are from us, and therefore how far back in time we're actually looking when we look at these galaxies. Now, it's interesting to note that this study, which was published just a few days back, one of the co-authors on the paper, and I want to put a plug in for the University of North Dakota here, one of the co-authors is Elijah Matthews, and he did his undergraduate degree here in the Department of Physics and Astrophysics at UND. And so he went on to do his graduate work at Penn State, so he is part of this study.
Yep.
So it's
Come join us.
Yeah, so it's nice to see students going out and being successful.
Absolutely. That always tickles you and makes you go, yes.
So the answer to this story is wait and see. We have to have the confirmation, and once we can confirm it, then we need to get down and busy to figure out how galaxies can form in the order of several 100 million years.
Right.
Okay? It's not like you push back the age of the universe. Oh, let's just make the age of the universe instead of 13.8 billion. Hey, let's give them a few extra billion years to form. Let's push it to 20 billion years. Then if you do that, then it's like, okay, where are those objects around us today that are 15, 16, 17, 18 billion years old? There aren't any.
Right.
You see? So if you lived in a universe that was 20 billion years old, as an example, where are the things that are 19 billion years old or 18 billion years old?
On that score, let me bring in what we're talking about here. If I'm not mistaken, in some of the globular clusters, there are some red dwarfs, some M-class stars that are on the age of some of the oldest objects in the universe in our own galaxy, right?
Yeah, so there is a history here.
Okay.
Back in the 1990s, when people were studying globular clusters, so these are these clusters of stars that contain anywhere up to hundreds to even a million of stars, all gravitationally bound together, and there's nearly 200 of them that are in orbit around our Milky Way galaxy, and we find globular clusters around other galaxies as well. In the 1990s, what was determined was the age of the globular clusters was actually older than the universe itself. Now, there is a way of dating globular clusters because when globular clusters form, all of the stars form at approximately the same time. Now, stars, because we've studied stars for many hundreds of years now, stars don't all live the same length of time. They have different life expectancies, which is dependent directly on their masses. A massive star can live as short as just a few million years, and a very low mass star can live up towards 1 trillion years. Okay?
Mm-hmm.
So if you have a collection of stars, let's say you form, for sake of argument, 100,000 stars at approximately the same time, within, let's say, 500,000 years. Okay. What you'll notice if you look at that population of stars at the different slices of time, let's say 1 billion years later, 2 billion years later, 3 billion years later, and so on, you'll notice that the massive stars evolve away first because they go through all their life cycles and end up exploding as supernovae and turning into various objects like neutron stars and black holes and so on. And what you're left with then are these sort of low mass stars that are happily converting hydrogen and helium in their cores, like our sun is doing presently. And so we can actually note that over time, the population of a star will change as the stars evolve differently depending on their masses. So at any given moment in time, if you made that assumption that all stars formed at approximately the same time, by knowing which stars are around still today or which ones occupy different phases of their lives, you can put a reasonable estimate of the age of that population.
Right. Having done this type of calculation before, I can sit there and say the main sequence usually sits here like a diagonal across your graph. And what happens is there's this branch off. In fact, that's exactly what it's called, where the old stars are branching off of that main sequence where stars like our sun are. And so you get this branch off, and where that branch off is happening tells you the age of that cluster of stars.
Well, in fact, Robert, we should do a podcast
On this.
on stellar evolution.
Absolutely.
Because sometimes people, they don't understand that we know a lot about how stars evolve.
Right.
And so this is work that's been done for many, many decades now. Very detailed scientific work.
Mm-hmm.
And so that's something that would be truly amazing what we know.
And how we know it.
And how we know it.
Really, I think I could actually dig up some of my data and show this. It doesn't look as pretty as the, graphs they put into the textbooks and everything, but you can see it happening.
Right. So the overall point is then, by looking at globular star clusters, we have a good understanding of how old they are. And in the 1990s, several of these globular clusters displayed ages that were older than the universe itself.
Right.
Okay. That would be like you're older than your mother. And you're like, what? How can that happen? Well, it can't happen. So there's something wrong. Either the age of the universe is wrong, the age of the globular star clusters is wrong, or maybe, of course, you have both of them
Or
wrong,
maybe both of them wrong.
right? What was discovered is we had the age of the universe wrong. Why? Because in the late 1990s, in particular in 1998, we discovered dark energy. And when you add that component to the overall composition of the universe, and then calculate what does that mean in terms of now the age of the universe, all of a sudden the universe is older than the globular clusters.
Right.
You are now younger than your mother. And you'd go, whoo! Thankfully, things make sense now logically, right?
Right. And this is where you may have heard of some paper on the Methuselah star, as it was called, and things like that. And it's like, no, it was just a matter of we had a few numbers wrong in our calculations. It wasn't, and when we made the observations, we go, oh, hey, and correct that, and now things work.
But that's how science works.
Absolutely.
Right? If you think the universe is 14 billion years old, which is approximately what we think it is today, and you find population of stars, for example, that are clearly 18 billion years old, there's a problem.
There's a problem.
Right? So that's telling you need to go and fix things. That's how science works. It's a self-correcting type of thing.
And you don't fix them by just saying, well, we'll make this number this. You go out and you make observations. You see what's going on. Like if we would have thought it was a problem with the age of the globular clusters, we would have retaken all of that data. We would have looked at our evolution, our theories on evolution of stars, and we would have recalculated the age based on those new data, those new observations. As it is, it turns out we made some new observations of the universe and said, whoa, wait a minute, there's something else going on here. And it pushed the age of the universe back. Will that happen again? Maybe, maybe
Right.
not.
So if we want to give galaxy formation, which is what we're starting
What we were talking about.
if we want to give galaxy formation an extra few billion years to take place, we have to push back the age of the universe. So now instead of being roughly 14 billion years old, it's going to be 16 or 17 or 18 billion years old. And then the question we would have is, why don't we see anything around us locally that's of that type of ages? That's more than 14 billion years old. Where are those objects?
Right. Because at that point you're saying, what we're pointing out is why aren't there any globular clusters or other old stars that are that old? And
Right. I mean, that's one aspect, right? There are other aspects
there are
too.
other aspects as well.
Yes, if you analyze in detail the leftover heat from the Big Bang, the cosmic microwave background, that gives you information about the age of the universe. The expansion rate itself can tell you about the age of the universe. For example, a very silly example that I like to use in class to illustrate the point is, imagine that the moment of a human being is born, they grow at a rate of 1 foot a year. So if you're walking through the airport someday and you meet up with friends that you've never seen for many years, and in the meantime they've had a child, and recently had a child, and you're like, oh, you have, oh yeah, look, and then you're like, oh, I know how old you are, you would say to the parents of the child, and they're like, how do you know that? Well, just a minute, I will measure the height of the child. The child is 3 feet high. You're 3 years old. And they said, well, how do you know that? Because I know humans grow at a rate of 1 foot a year. So if you're 3 feet high, you must be 3 years old.
Right.
Okay? I mean, like I said, that's a silly example, but that's what you can use when you think about the universe. If you know the rate of expansion, you can work backwards in time to get an idea when it all began.
Right.
And that's consistent with this 13.8 billion years.
And again, The expansion rate of the universe is an observed quantity. We know how fast that is happening. So the only other option is that that rate changed throughout time, but we have observations that certainly this.
Well, be careful on that because we know the rate does change with time.
Right.
Okay? And so one way to think about it is, number one, we have the influence of dark energy. Right. So that's an accelerated expansion. So the expansion rate is increasing with time. But also the thing is, when you think of right after the Big Bang, the universe is expanding at a fast rate. But because of the combined gravitational influence of all the matter and energy in the universe, the expansion rate started to slow down immediately after the Big Bang, like throwing a rock up in the air. As soon as that rock leaves your hand, it immediately starts slowing down because gravity is pulling it downwards, pulling it back. So we know the expansion rate has been slowing down since the Big Bang, but what we didn't know until the end, 1998, was that expansion rate, roughly about 5 billion years ago, has been now starting to increase.
Okay.
So in the beginning, the dark energy is at a very low level, so it did not dominate the expansion rate of the universe early on.
Right.
It's only in really recent times has the density of the universe dropped to the point where now we're in this dark energy dominated phase to the universe. So the expansion rate has changed. It's not been the same since day one.
But it's changed in a fairly predictable fashion.
Yes, that's the point. We know how it has changed, so we can work backwards in time with that expansion rate and how it's changed with time and predict the age of the universe. That is consistent with 13.8 billion years. If all of a sudden the universe is now 18 billion years old, that now is not consistent with the measured expansion rate and its change with time. So now you might have fixed one problem,
but you created another.
But you created a monster on the other hand of all these additional
You fixed
problems.
a tiny problem to create a Godzilla.
Yeah.
And I would like to point out something on there. Folks, down is not north or south. Down is towards the center.
Right.
Just going to throw that out there. Yeah.
So that's the sort of the big news that was happening this week, I noticed, when we talk about galaxy formation. So it's very exciting observations.
Mm-hmm.
It's hopefully going to give us additional information that we otherwise didn't have about how galaxies form to begin with. And that's, the textbook will probably be rewritten with observations yet to come from the James Webb Space Telescope on the formation of galaxies.
But again, it'll be the formation of galaxies that's rewritten, not Big Bang cosmology that's rewritten.
Right, or it's not going to be doubling the age of the universe all of a sudden overnight.
Right, because, yes, I've already heard somebody blabbing about how this calls into question the whole big, no, it really doesn't.
No, I mean, that obviously captures people's attention if you make outlandish claims, of course.
You click.
Yes, well, all of that's obviously on the internet nowadays, and so you can get away with that. But yeah, and so we'll see what happens and with that issue going forward. So it's going to be interesting.
So it's going to be interesting.
Now, Robert, you had some other items on that list.
Yes, let's go back to that list and let's look at some of them. So we talked about Quar and how it does not defy our understanding of gravity. We've now talked about the universe breakers, which do not break the universe. They just break our understanding of galaxy formation. So I'm going to go with these here next. Which you probably can't see my cursor, but piece of the sun breaks off near the North Pole, leaving scientists stunned. And in conjunction with that was powerful X-class flare spat out a rare solar tsunami. You can hear it smashing into Earth. And our sun is lighter than ever, and the problem is getting worse. I love that one, because the sun is getting lighter. It is converting hydrogen into helium, which involves a slight mass loss, a mass that is then changed into energy in the form of photons, in the form of gamma rays specifically, which then filter out slowly to be radiated in the spectrum of visible and infrared, radio and microwave, and visible and ultraviolet light that we can see here on Earth. So what's the big deal? The big deal is they're trying to make it sound like the sun just suddenly lost a lot of mass and it's getting worse. No, it's going to take 4.5 billion years for it to really become a problem.
Well, when you think of mass being converted into energy through standard nuclear fusion processes, which ultimately is where our energy comes from that we enjoy as the heat and light that we receive here on the Earth. I forget the exact number, but the sun literally crunches through tons and tons and tons of hydrogen per
Every
second. Per second.
So, yeah, the sun's losing what sounds like to us an incredible amount of mass. To the sun, it's like, something happened? Something going on?
In fact, along with that, of course, is that the sun is leaking material. We call it the solar wind. But that would take, somewhere more than 10 billion years at the present rate for that solar wind to
eliminate
yeah,
the
it's like I think it's on the order of like 100 billion years or something like that. So it's insignificant.
It's insignificant. So what the others? Let's go back to them. This solar tsunami and this part of the east of the sun breaks off at its North Pole. Why was that a big deal? Well, most what we call flares and prominences do occur more down towards the equator. Okay? Has to do with a lot of different factors, angular momentum, blah, blah, blah. I could do a whole podcast on that sort of thing. So it's really rare to see a big one on the northern or southern part of the sun. Well, guess what we saw? A big one. Notice I say it's uncommon. It is not unknown. It is not even a rare phenomenon. It's just, oh, wow, look, it broke off there instead of down towards the equator. And that's what happened. But these news articles make it sound like, holy crap, this never happens. Yeah, it happens. And then there's the whole smashing into Earth. Go ahead.
I was just going to say, so it's interesting to note the history behind some of these observations. So if you look at the sun in X-ray, so at X-ray wavelengths, you can see there are holes, as they call them, right? Cavities, and they're not cavities, but they're regions, dark areas on the sun where we see the emission of a lot of this sort of coronal mass ejection type of stuff.
And really all that is where the magnetic field is peeled back and opened up a pathway for it to fly.
Right, and the first good observations of that actually came from the Solar X-ray telescope that was mounted on Skylab back in the 70s.
Oh.
So that's where we got it, because X-rays don't make it to the surface of the Earth. They're blocked by our atmosphere, mainly the ozone layer. And so if you have an X-ray telescope, the joke is, I could afford the X-ray telescope, but I couldn't afford to put it in space. So you may as well just stick it in a museum because it's useless on the ground to look at astronomical objects. So back in the 1970s, early 1970s, when the Apollo project wound up and men stopped going to the moon, but the next big thing that NASA partook in was the development of Skylab, so a orbiting research laboratory. And one of the things they put on Skylab was a solar telescope to make observation at X-ray wavelengths of the sun. And that, as well as some unmanned spacecraft that have gone up, gave us our first really good detailed observations of really the violent nature of the sun itself. When you look up at the sun in the daytime, from the ground, of course you wouldn't look up at it nighttime, right?
Right.
When you look up at the sun on a nice clear day, how's that? You see this nice sort of homogeneous sphere in the sky. It looks like a disk. And it doesn't seem, you can't see anything on it. It looks nice and smooth and uniform. And it looks like the same sun you saw the day before, if it was clear, or the year before, or the 10 years before, and so on. And yet, if you look at the right way at the sun, you'll see it's a very dynamic type of environment. There's things changing on the surface all the time. For example, if you take a solar telescope on the ground and look at optical wavelengths with the proper filtering, never look at the sun without proper filtering. Okay, that's one way you can lose your eyesight instantly.
Right.
So if you look at through a telescope with the proper filters at the sun, you can see its surface, it's boiling, the convection that's occurring. So you see things changing on a relatively very short time scale. You just can't see with your eye. You don't have the resolution to see that detail. Of course, you can't stare at the sun long enough to see that either.
Resolution. Resolution, folks, comes from the width, the wavelength you're looking at, but as well the aperture of your telescope. Your pupil of your eye is about 8 millimeters. The smallest telescope I've ever seen is about 40 millimeter. So 8 millimeter versus 40 millimeter. I can see a lot finer detail with even a tiny telescope.
Right. And so it's really since the 1970s that we had a detailed view of what was happening on the sun itself. So this idea where there are regions on the sun, whether it's towards either the poles or in the equator, that are emitting more of these particles, the solar wind. We have fancy names called coronal mass ejections. The sun burps or hiccups at certain times, and it releases these particles. I mean, you can go on the internet and see images taken from various spacecraft that NASA has, constantly monitoring the sun to see this in sort of in real time, a type of effect. And so we know this stuff has been going on for many decades now, and so it shouldn't be a surprise.
Right. And I just put on a website that you can go to look at in the chat to look at the current sun. It's called spaceweather.com.
Right, exactly.
Wonderful site.
Exactly. So things like that can keep abreast of what's happening on the sun. But, whether or not we're talking about the sun, whether or not we're talking about the formation of galaxies or anything else, I don't know, is it that the reporters, I don't want to pick on other people, but I will.
Okay.
Okay. Is it that reporters that write up these stories? I mean, someone has to write the story and put it on the internet.
Right.
Okay. We're assuming some AI is not doing that. That might be the case in the future.
That might be coming.
Yeah. So we're assuming that there's an actual live human being that's writing up these stories and putting it on the internet. Do they not have the science literacy to know better when it comes to these headlines or some of the statements that they make in their stories?
And from what I understand from some people in the business that I do know, the answer for the most part is no. They are reporters, they are journalists, and you do have some out there who have some science background, but for the most part, no. They have their general core requirement science classes, and that's it.
And see, that's a problem. We're such a scientific society, and more so going forward in time into the future, of course. I think it becomes extremely important that people understand at least the basic fundamentals of the science themselves, so they can tell when they read different articles. For example, you could show them an article or a headline, right, of an article that was written, or maybe it's just a faked one, and say, what do you think of this? And they should be able to look at it, read it, and say, no, this doesn't make sense. This is preposterous. I would never, put my name behind that type of thing. Until we have people that can make those type of judgments, we're in a little bit of difficulty.
We're in a seat, and I agree. I think that's part of our problem nowadays is, we've got journalists who want to, we need to give airtime to both sides of the story. No, you really don't. Okay, when 90% of scientists are saying one thing and only 10 are saying the other, both sides do not deserve, need, or require, or any other term you want to put to it, equal airtime. Okay.
Yeah, I mean, I even seen this in television news. I won't mention the station or the company.
Right.
But in particular, there was a company that I'm thinking about who had an actual science journalist, somebody who knew a bit about science to the point where they could conduct themselves on live events or do interviews, and they eventually got rid of them. Like they just closed that part of their company, right? And it's like we need that. We should be opening up that part of the company, not closing it down.
As you said, we're becoming such a technologically and science-based culture that shutting that sort of thing down or naysaying it because it's not saying what you want to hear, well, that's getting us into some of the problems we have.
Yeah, that's a disservice to society in general, in my opinion.
Right.
And so that's something.
At the same time, focusing on some of the more sensational aspects of things is just as bad. It's like if it sounds sensational and it's coming from science, it's probably fertilizer. Okay. You could probably go spread that out in your garden.
Now, talking about fertilizer, that leads into something else you had on that list, and that's regarding the asteroid. You want to say something about that?
Oh, yeah. So let's look at that headline. Asteroid Ryugu is rich in organic molecules that can be building blocks of life. Now, the reason I highlighted that one, the reason I put that one on the list, is not because there's anything terribly sensational about it or terribly wrong. Organic molecules are the building blocks of life. Except what was found on this asteroid and its materials is simple amino acids, nitric acid, some benzenes and ethanols and things like this, various alcohols and esters and so forth. Can you make the building blocks of life out of these things? Yes. Are they the building blocks of life? Not really.
Well, here's an important question.
Right.
Can you take those building blocks of life and make life? Show me that in a laboratory.
Show me that in
Robert.
the laboratory.
We,
And I'm right there with you. Show me that.
Yeah.
We can't do it.
we
yet.
can't do that yet today.
Right.
So we know what the fundamental building blocks are, but we don't know how to assemble them
How to assemble them.
to make life.
And that's kind of where I was going with that. And it's like is the word disingenuous to say that it's rich in organic molecules, the building blocks of life. I mean, there are ketones that if you put those into a living thing, the living thing dies. So saying that organic molecules are the building block of life, a ketone, by the way, is a organic molecule, is just kind of pushing things with me. You know?
Well, it's almost like saying, oh, come to my house. There's a bag of sugar on the counter. There's a bag of flour, and there's there's a couple eggs laying there. There's my cake. Now go ahead and eat it.
Right.
You're not gonna, do that, right?
Right.
Obviously, those things need to be
Now,
combined in such a way to get cake.
We are not naysaying the science behind that. Okay, what I'm naysaying is the headline. It makes it sound like there's more there than what there really is.
Right.
And, I have little doubt that, science is getting in there where we know now that membranes can form spontaneously to encapsulate materials. Well, once you concentrate materials, you can start putting them together a lot faster. So, we know kind of where these molecules get together and form things, but we're not there yet.
Well, here's another important consideration. We can use radio telescopes and look for the presence of different molecules,
Oh, yeah.
right, in interstellar matter, the gas and dust clouds that we see
Yes.
in our galaxy. And we see the presence of over 200 different types of molecules, including these very fancy molecules, right? Benzene and amino acids and so on. And you know what else they've discovered in space also? And this made headlines when it was discovered for the first time.
I think it was ethanol.
Yeah, it was alcohol. It's the type.
alcohol.
It's the type you can drink without going blind.
Yeah.
Okay.
We could go throw a kegger in the space club.
Right. So you don't have to bring that with you on a long interstellar voyage. You can just siphon off of from the cloud somewhere on the way, right? So yeah, all these complex sort of chemical molecules and reactions and reactants that we find that we need for life to arise, we find that in the space between stars. That's why it's part of this discussion of whether or not life is unique here on Earth. You would say life only arose here on Earth, period. Why? Because there's no other place in the universe that has the ingredients necessary for life. Right? Wrong. We find those ingredients everywhere. So what is the chance that life only assembled those ingredients in the right way here on Earth and nowhere else? None of the other trillions and trillions and trillions of planets that exist in our universe.
Right.
That's the statistical argument that we are probably not alone. Doesn't say where they are, of course.
Doesn't say how far away they are.
And all these other questions that we talked about already in the past.
Right.
But certainly the raw ingredients to form life is everywhere.
It's everywhere.
Including on this asteroid, you see?
Which gets back to our discussion of the Drake equation and the Fermi paradox that we had a few episodes back. This is why I make my statement of my number that goes into the life forms factor in that Drake equation is going to go down significantly if we don't find life existed on Mars at some point. I don't think it's there now, but I think it probably was at one point. I think the conditions were there. And I think we'll find it in Europa, down underneath the ice sheet, in the ocean we now know is there. So if we don't, I guess I should say I hope we're finding it there. Because if we do, then now we've got multiple places in our own solar system where life developed. And holy cow, life is going to be everywhere. But if we don't, then I'm back to square one and agreeing with people. Life is a fairly rare thing.
Well, remember what NASA had said in the last several years, was as part of their program to explore Mars, was follow the
water?
Yeah, follow the water.
Yeah.
So look for the presence of water,
Mm-hmm.
and that would be a place that you would look for the presence of life.
Why is water so important as far as the development of these things?
Yeah, well, think about us.
Right.
How much do we contain in water?
Why is water so necessary, though? Why is water the big thing? And that is because it's a good solvent. You can dissolve a lot of different things in different quantities into water. And so now you can get them mixing in, dissolved into the water. They're now mixing around, and they can combine. And so water, because of its solvent properties, is why it's conducive.
Now, can you think of an unusual location in our solar system which water has been discovered in the past?
Well, the most unusual one I can think of is Mercury.
Go more unusual than that.
Really?
This is called
Water more-
Stump Rubber Time.
Yeah, because you've stumped me, because that's
Do,
the
do,
one.
do, 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 do,
The
do.
moon has found it too. But I
Oh.
would consider Mercury more extreme than
The
that.
clock is ticking, Robert.
Oh no. I wouldn't say the outer solar system either, because we know water is there.
No, you're getting colder when you go out that far.
Venus's atmosphere?
No,
Okay.
you're getting warmer, but not warm enough.
Warm enough.
The surface
So
of
the sun?
The sun.
Yeah.
Yeah.
I kind of knew that. The reason I kind of knew that is because one of the sources of opacity, of absorption of light in the sun's spectra, is the H
Negative.
negative ion,
Yep.
which means hydrogen with an extra electron, and you only get that with water.
Yeah. So there have been observations that have been done in the past, mainly of sunspots, where they detect the presence of H2O, water.
Right.
So
And David Leach has asked a question. Water on Mercury, is it all in the gaseous state? It is not. It is down at the bottom of craters that never see the sun directly overhead. So there it is in the form of ice again, but it's down in these very shadowed craters. And the only reason it can exist even there is because Mercury has essentially no atmosphere. And so there's no way to convect heat down in there. Rock is not the best conductor of heat. And so the heat can't conduct down into the bottom of these craters. So the only way it can be heated up is by radiation, and the sun never gets down into the bottom of those craters.
in fact, we use that same explanation for what we think is happening on the moon.
On the moon.
So the prime real estate on the moon nowadays is actually the south pole of the moon itself, because there's regions there, as far as we can tell from mapping, from orbiting spacecraft around the moon, is that there are permanently shadowed regions inside of craters that may have the presence of ice. In fact, we've done measurements that indicate that there's ice there. And so that would be a great spot to go setting up a base, for example. Imagine like you have a base in Antarctica. Let's have the same type of base on the moon. Well, if you put it somewhere where we have ice, that helps, the sustainability of the group that we have on the moon, you see.
Water has a density of 1,000 kilograms per cubic meter. It's a lot of weight saved if you do not have to take water with you.
That's right. If you're not transporting water from the Earth to the moon, if the water is already there and we find a way to just extract it from the ground and purify it to the point where we can drink it, then that saves a lot of money, basically.
A lot of money allows for a lot of other types of cargo to be put in there.
That's right, exactly.
But I think we're about out of time, so I know
Yeah.
we got a quote. So.
Yeah, so we're getting to the end of this. So our next podcast will be on Tuesday, March the 7th at 3 p.m. Central Standard Time. And I'm going to leave you with a quote, and the quote is from Albert Einstein this time.
Woo.
And Einstein said, "A person who never made a mistake never tried anything new." So thank you very much for watching and for listening, and we'll see you next time.
Thank you for asking questions. Thank you for showing up. Y'all have a wonderful time.